On November 14th, 2025, something emerged from behind our star that shouldn't exist. An object, intact, changed. 3 I Atlas had vanished into solar fire just days before, close enough to feel temperatures that vaporize metal, that strip atmospheres, that shred ice into molecular dust. Every model said it would fragment. Every calculation predicted destruction. It did not break, and when it reappeared on the other side, streaming away from our star with a tail nobody expected, scientists across 3 continents stopped what they were doing and stared at their screens in silence. Because this wasn't supposed to happen. The rules of cometary physics, tested across centuries of observation, said an object like this, traveling at such velocity, passing so close to solar radiation at its most intense, should disintegrate, should become a cloud of fragments, should leave behind nothing but a debris trail and a footnote in astronomical records. 3 I Atlas ignored those rules completely, but the real shock was still hours away. Let me take you back to the moment of realization. November 14th, morning light spilling across observatories from Chile to Australia, telescopes tracking the predicted exit point where 3 I Atlas should emerge, if anything emerged at all. The betting among astronomers wasn't optimistic. Most expected fragmentation. Some hoped for partial survival, maybe a large fragment, maybe 2 or 3 pieces tumbling away from perihelion. A few optimists thought the nucleus might stay mostly intact, but show severe scarring, mass loss, structural damage. Nobody predicted what actually appeared. The first images came through Space.com's release just hours ago, and they showed something unexpected. The tail wasn't scattered. It wasn't diffuse or chaotic like a dying comet's last gasp. It was surprisingly narrow and well-defined for a comet emerging from perihelion, sharper than before it disappeared behind solar fury. A needle of ionized gas stretching millions of kilometers into space, structured in ways that challenged initial predictions. Not the broad, fuzzy exhaust plume typical of stressed comets. Not the asymmetric spray of an object shedding mass unevenly, but an organized stream, almost geometric in its precision, extending backward along the object's trajectory, like a cosmic contrail. The scientists at the European Space Agency saw it first, then Harvard, then teams across 6 time zones, all reaching the same conclusion independently. 3 I Atlas had not only survived, it had transformed. Today's Economic Times published quotes from astronomers using words they rarely use: shocked, baffled, unprecedented. One researcher described it as the most structurally stable perihelion passage we've documented for any long-period visitor. Another admitted they'd expected to be writing an obituary, not an observational report. Because here's what should have happened. Solar radiation at that distance doesn't negotiate. It destroys. Objects passing that close to our star experience temperatures exceeding 2,000 degrees Celsius. Ice sublimates instantly. Structural weaknesses become fracture points. Gravitational stress tears fragile bodies into debris fields. The tidal forces alone should have been devastating. 3 I Atlas passed close enough that one side of the nucleus experienced significantly stronger gravitational pull than the other. For most comets, that differential stress is enough to crack the nucleus like an egg. We've watched it happen before. Comet Ison in 2013 disintegrated completely. Observers watched it approach, bright and promising, only to see it emerge as a thin stream of dust with no coherent nucleus remaining. Dozens of long-period comets shattered into fragments, some breaking months before perihelion, others surviving the approach only to fracture on the way out. But 3I Atlas, completely intact, the newest images show a nucleus that appears structurally stable, no debris cloud, no fragmentation signature, no signs of catastrophic breakup, just a single coherent object with a tail structure that's sharper and more organized than models had predicted. The contrast with expectations couldn't be starker. Where astronomers anticipated chaos, they found order. Where they expected destruction, they documented resilience. If you spotted this first, what's the very first thought that hits your mind? Think about that for a moment. An interstellar visitor, possibly billions of years old, carrying frozen chemistry from a star system we'll never see. Traveling through the galaxy's radiation fields, cosmic ray bombardment, an empty cold for eons, and it survives an encounter that destroys objects born in our own cosmic neighborhood. What else have we underestimated about interstellar objects? What are the assumptions about comet structure, about ice cohesion, about thermal tolerance might be based on a sample size that's too small to capture the full range of possibilities? But visuals were only the beginning. The numbers told an even stranger story. Here's what we know from verified observations. Early spectroscopy released in the latest RxIV preprint shows something unexpected in the coma, the cloud of gas surrounding the nucleus. Carbon dioxide dominance, not water, not the mixture we see in most solar system comets, but CO2 as the primary volatile present in concentrations that dwarf everything else in the spectral signature. This tells us something profound about where 3I Atlas was born. Carbon dioxide freezes at much lower temperatures than water. For CO2 to dominate, this object had to form incredibly far from its parent star regions, so cold, so distant, that even water ice would be a minor component. We're talking about formation zones in alien solar systems that make our Kuiper belt look warm. Regions where temperatures hover just a few degrees above absolute zero. Where sunlight, if you can call the dim glow of a distant star, that provides almost no heat whatsoever. In our solar system, such conditions exist only in the most remote reaches of the Oort cloud, and even there, comets that eventually fall inward tend to be water-dominated. 3I Atlas suggests formation in an environment even more extreme. The European Space Agency refined the object's trajectory using data you wouldn't expect. Mars, instruments orbiting the red planet, tracked 3I Atlas during the days. It was unobservable from Earth, hidden behind our star's overwhelming glare. This wasn't the primary mission for those spacecraft. They're designed to study Mars, not track interstellar visitors. But when opportunity presents itself, astronomers adapt. And the geometry was perfect. Mars happened to be positioned where its orbiters could maintain line of sight to 3I Atlas, even as Earth-based telescopes lost it in solar glare. And those observations revealed something subtle but significant. Tiny course adjustments. The refined orbit shows minute deviations from purely gravitational predictions likely caused by natural outgassing. According to ESA scientists, this is normal behavior for active comets. Gas jets push against the nucleus, creating small but measurable changes in trajectory. It's called the rocket effect, and it's one of the primary reasons why predicting comet orbits with extreme precision is so challenging. But the precision of the measurements reveals just how active this object remains. Fresh spectroscopy shows multiple emission lines. The coma is thick with sublimating gas. Jet patterns visible in the newest photographs suggest organized venting from specific locations on the nucleus. And here's where it gets interesting. Those jets aren't randomly distributed. They appear clustered, suggesting that outgassing is concentrated in specific regions, possibly areas where surface composition differs or where subsurface ice has different thermal properties, or where the nucleus structure allows gas to escape more easily. JWST and Hubble analysis notes, not full papers yet, but preliminary observations, show no major dust explosions, no catastrophic release events, just controlled, sustained activity. The distinction matters. When comets fragment, we typically see sudden spikes in brightness as fresh ice becomes exposed and sublimates rapidly. We see expanding dust clouds, asymmetric coma structures, secondary nuclei separating from the primary body. None of that appears in the 3I Atlas data. Meerkat radio observations detected natural gas outflow patterns exactly where optical telescopes saw the jets. The correlation is nearly perfect. Radio emissions from ionized gas molecules align precisely with visible light observations of jet structures. Everything points to an object that's responding to solar heating the way comets do, but surviving what comets can't. What does this say about objects formed under other stars? About the diversity of ice compositions in the galaxy? About how primordial material from different stellar environments might behave when exposed to our star's radiation? Which outcome do you think is most likely now? A. The activity fades and the object stabilizes. B. The jets grow stronger and the tail changes again. C. Something unexpected appears in the next images. And here's where the contradictions emerge. The survival itself is the first puzzle. Astronomers who study comet fragmentation have models, tested models, models verified by decades of observations showing exactly how heat, stress, tidal forces, and rotational strain tear these objects apart. These aren't speculative frameworks. They're built on real data from hundreds of observed comets, refined through comparison with laboratory studies of ice mechanics, validated by matches between predictions and outcomes. 3I Atlas should have fragmented based on those models. The thermal stress alone should have done it. When one side of a comet nucleus faces intense solar radiation while the other remains in shadow, the temperature differential creates internal stress. Ice expands and contracts at different rates, depending on temperature. Over time, or sometimes quite suddenly, that stress finds weak points and the nucleus cracks. But 3I Atlas shows no evidence of cracking. Preliminary modeling now suggests the nucleus must be unusually dense, structurally cohesive, in ways that challenge what we know about typical comet formation. Perhaps it's older than any solar system material we've studied. Perhaps primordial ice from the galaxy's youth freezes differently, bonds more tightly, resists stress better than material formed around our own star. Perhaps the formation environment, those ultra-cold regions far from a parent star, creates ice with different crystalline structures, different mechanical properties, different responses to thermal stress. We don't know. The tail structure presents another curiosity. That sharp, well-defined ion tail requires specific conditions: strong magnetic field interaction, consistent solar wind pressure, uniform outgassing. Ion tails form when ultraviolet radiation from the star ionizes gas molecules in the coma. Those charged particles then interact with the star's magnetic field, carried away by the solar wind in a process that creates the characteristic straight tail pointing away from the star. But the degree of organization in 3I Atlas's tail is unusual. Most comets show more turbulent structures, kinks, waves, disconnection events where parts of the tail separate and drift away. The interaction between solar wind and comet coma is typically chaotic, producing beautiful but complex patterns. 3. I-Atlas's tail is remarkably clean. But the newest images show multiple narrow jets, not the wide-angle bursts typical of active comets. ESA modeling suggests the jet pattern might indicate a spin state change during perihelion. The object may have altered its rotation as it rounded our star. What pattern do you think we'll see next? More symmetry or complete turbulence? Thermal stress could have carved new vents, opened fresh pathways for gas release. When ice sublimates rapidly, it can erode surface layers, creating channels and vents that persist even after the initial outburst subsides. But rotational changes require asymmetric forces, uneven heating, internal pressure variations. If the nucleus did change its spin state, and that's still a hypothesis, not a confirmed observation, it means the internal structure is dynamic. That gas pressure beneath the surface was strong enough to alter the object's angular momentum. That the nucleus isn't just a passive lump of ice responding to external heating, but an active body with internal processes we don't fully understand yet. Each explanation creates new questions. And then there's the speculation. Some outlets briefly speculated about unusual structure, but major observatories immediately clarified that there is no evidence suggesting anything beyond natural comet physics. All mainstream research teams agree. Every observation is consistent with an interstellar comet responding to solar heating. Abraham Loeb mentioned examining outgassing patterns more closely. Other astronomers point to natural jet activity as the clear explanation for any orbital variations. The mystery isn't whether this object defies known physics. The mystery is why an ancient ball of primordial ice behaves differently from comets we've studied in our own system. Because here's what bothers me most. We thought we understood comets, dirty snowballs, we call them. Simple objects governed by straightforward physics. And then something arrives from beyond our cosmic neighborhood and survives conditions that should annihilate it using physics we already know, but in combinations we haven't observed before. Maybe we don't understand the full range of comet behavior yet. Maybe what we've observed for centuries in our own solar system is just one narrow expression of how ice and dust can organize itself across the galaxy. Maybe the universe builds things in ways we're only beginning to catalog. Now, pull back for a moment. Look at what's happening here. An object likely older than any solar system material we've studied, forged in darkness around a star we'll never identify, traveling through the galaxy for longer than complex life has existed on Earth, and it passes through our solar system at exactly the moment we have telescopes capable of studying it. The timing is almost absurd. 50 years earlier, we would have missed most of this. The spectroscopy wouldn't have had the resolution. The precise orbital tracking wouldn't have been possible. The jet imaging would have been crude at best. We might have detected a fuzzy blob moving against background stars, measured a rough trajectory, and filed it away as unusual comet, possible long period origin. That's it. No composition analysis, no jet mapping, no understanding that we were looking at material from another stellar system entirely. 50 years from now, 3I Atlas will be gone. Back into the dark, unreachable. Its trajectory will carry it out beyond Neptune, beyond the Kuiper Belt, eventually beyond the heliopause, where solar wind gives way to interstellar medium. And then it continues outbound, cooling, returning to the frozen silence it knew before our star briefly warmed its surface. Where will it go? We can calculate its trajectory for centuries, maybe millennia, But eventually, gravitational perturbations from passing stars will alter its course in ways we can't predict. It will wander through the galaxy, perhaps for another few billion years, until it encounters another stellar system. Or until it doesn't. The galaxy is vast. Most of it is empty. The odds that 3I Atlas will ever again pass close enough to a star to experience what it's experiencing now are vanishingly small. But right now, in November 2025, it's close enough to see, and what we're seeing is a glimpse of how other solar systems work, what ice looks like when it forms under different stars, how chemistry freezes in regions we'll never visit. This object is a messenger, not an intelligent message, nothing designed or intentional, but a physical record of processes happening in stellar nurseries across the galaxy. The CO₂ dominance suggests ultra-cold formation. The structural stability suggests something about binding forces in ancient ice. The survival suggests durability models didn't fully predict. Every measurement is a data point about the galaxy itself. Every spectral line tells us about the chemical conditions in a star system we'll never see. Every jet pattern reveals something about how primordial ice responds to thermal stress. Every trajectory deviation teaches us about outgassing dynamics in objects that formed outside our cosmic neighborhood. How many other chemical signatures exist out there that we've never encountered? Think about how small our sample size has been. Until 2017, when Oumuamua arrived, we had studied exactly 0 interstellar objects. 0! For all of human history, for all the centuries we've studied comets, all the decades we've had modern astronomy, all the years we've sent probes to examine solar system objects, up close we had only ever examined material that formed around our own star. Now we have two visitors out of billions that must be crossing through our solar system over geological time. 2 glimpses of chemistry and physics from elsewhere. That's not a survey. That's barely a peek. And yet already, both objects have violated our expectations in different ways. Oumuamua, with its acceleration, that outgassing likely explains, though the exact mechanism remains debated. 3I Atlas, with its unexpected survival and unusual composition. Maybe the lesson isn't about aliens or advanced technology. Maybe the lesson is humility. The universe is stranger than we thought, richer, more varied in its expressions of how matter behaves under gravity and heat and time. We built our models based on what we could observe. And what we could observe was limited to our own stellar backyard. 3I Atlas is teaching us that the backyard is not representative of the whole neighborhood. The timeline ahead is tighter than you think. The next 7 to 14 days will be critical. Astronomers expect several phenomena as 3I Atlas continues moving away from our star. Stronger tail ionization as solar-wind interaction continues. The object is still relatively close, still bathed in intense radiation and charged particles. The tail should continue developing, possibly becoming even more pronounced as outgassing continues and solar wind carries ionized gas farther from the nucleus. Increased jet asymmetry as different regions of the nucleus heat and cool. As 3I Atlas moves away, the heating pattern changes. Regions that were in shadow during perihelion now face the star. Areas that were actively venting might cool and go dormant. New jets might appear. Potential brightness spikes if fresh ice becomes exposed. If the surface layer has been eroded away in some regions, pristine subsurface ice, perhaps more volatile rich than surface material, could suddenly be exposed to direct radiation. That would trigger rapid sublimation and a temporary brightness increase. No debris cloud means stable nucleus, means long-term trackability. This is actually crucial for future observations. If 3I Atlas had fragmented, tracking the various pieces would become progressively harder as they separate and fade. But a single coherent nucleus remains bright enough to follow for months, possibly years. Harvard and ESA tracking confirms no threat to Earth. The object is leaving, following a hyperbolic orbit that will carry it back into interstellar space within months. The trajectory is well understood now. The Mars observations filled in the gaps. The orbital elements are refined to high precision. 3I Atlas will continue outbound, gradually fading as it moves farther from the star and farther from Earth. By early 2026, it will be beyond Jupiter's orbit. By mid-year, approaching Saturn's distance. Within a few years, beyond Neptune, but unusual behavior may continue. The jets might evolve. The outgassing might increase or suddenly stop. The tail structure might change again. Comets are unpredictable. They respond to heating in complex ways that depend on internal structure, composition, gradients, rotation, and factors we don't fully understand. An object can appear stable for weeks and then suddenly brighten due to a fresh outburst. Or activity can cease abruptly if vents become blocked or volatiles are depleted in active regions. Every observation is precious now, because soon, too soon, 3I Atlas will fade beyond detection range. Even the largest telescopes have limits. As distance increases and apparent brightness decreases, there comes a point where the object simply becomes too faint to observe meaningfully. We might maintain rough tracking for months or even years, but detailed spectroscopy, jet mapping, coma analysis, all of that becomes impossible. And we'll be left with photographs, spectra, and measurements. Evidence of something that happened once, something we're still working to fully understand. The data will be analyzed for years. PhD dissertations will be written comparing 3I Atlas to other interstellar objects, to solar system comets, to theoretical models of ice formation in different stellar environments. The real question isn't what 3I Atlas is. The real question is what else is out there. How many interstellar objects pass through our cosmic neighborhood undetected? How many chemical signatures are we missing? How many survival stories happen in darkness where no telescope points? We caught this one. We happen to be looking in the right direction at the right time with the right instruments. But for every 3I Atlas we detect, hundreds must slip past unseen, thousands perhaps. The calculations suggest that interstellar objects should be passing through the inner solar system regularly, maybe several per year, most too small or too faint to detect. Others simply not in the right position when we're looking. Messengers from distant stellar nurseries carrying frozen records of alien chemistry, surviving journeys we can barely calculate, most of them invisible to us, lost in the vast dark between stars. What do you think the next 14 days will reveal? Calm, chaos, or something none of us expect? At the next observation window, we may get the sharpest jet geometry yet, and I'll cover it here the moment it drops. Maybe the universe was never empty. Maybe we just never saw what was passing through.